Okay, so apparently I had a previous recording embedded on some of the slides, so starting over again. So there was a discrepancy between the PowerPoint that I showed this morning live in lecture and the PowerPoint on Canvas. Kindly pointed out that discrepancy to me. The one that's on Canvas is the one that we're actually using for course material. So now the one that I covered this morning was actually the old version of the lecture with less detail. And so none of the stuff that I covered this morning was a waste per se. It's just this one that I'm about to go through in recording is better because it goes in more depth and has more slides. So here we go. Okay, scotopic and photopic vision I covered in lecture. That's the difference between rods and cones, between contrast and color. Okay. So scotopic is your rods. It tells you can tell the difference between dark and light. Photopic is colors. You can tell the difference between reds and greens, basically. Okay. The two of them combined so that you can see red, green, and blue. All right, we went over that. We will cover that in this slideshow as well. We talked about how the LCD monitor is built and how the basis for the measurement lumen is the human vision spectrum. Okay, we talked about the cosine law in brief, but we didn't get to that in the lecture this morning. We talked about some of the QC tests for displays. We talked about the difference between ambient light and veil glare. And we're going to do that all again. And I'm going to try to keep it right around an hour, hour and a half. So, all right. So rods are used in your night vision. It's basically your contrast recognition. You can tell between sources of light and non-sources of light. And so your grayscale or the shading, how bright and how dark things are in your field of view, that's all your rods. Okay. Now your rods do detect blue light as well as some of your cones. But the rods primarily are trying to determine whether you would consider that bright or dark. Okay, that would be scotopic vision. Photopic vision is your daytime vision, your color vision. So it's the combination of the rods with contrast mapping underneath, but also adding additional information in the form of three colors and the intensity of three colors. Your cones are some types of cones are sensitive to red light, other types of cones are sensitive to green light, and then the third type of cones, along with the rods, are sensitive to blue light. And so human beings can essentially see three colors, and dependent upon the relative intensities of those, determine what your brain interprets the color to be. So I gave you the example of yellow. Yellow is actually stimulating the red sensitive cones and stimulating the green sensitive cones, but there's no stimulation for the blue sensitive cones. And so your brain says, okay, well, the red is lighting up and the green is lighting up. And so the wavelength must be somewhere between red and green. Because if it was just, if this color was red, only red would light up. If this color was green, only green would light up. But because I'm getting both red and green lighting up, it must be halfway between red and green. It must be yellow. And so your brain manufactures the color yellow and fills in the gap. Okay? The midpoint wavelength and the maximum sensitivity of your eyeball, both rods and cones, are stimulated by green light at about 555 nanometers of wavelength. Okay, remember from the wave equation, C equals lambda F. If you set lambda equal to 555 nanometers, that's the photon that stimulates both rods and cones in your eye. So green light is the one that gets the most uh, signal response going down your optic nerve because it stimulates both rods and cones. Okay. That's also where we benchmark the lumen at. So when we calibrate a photometer to measure intensity of a light source, we're measuring for 555 nanometer wavelengths or some area around it. It might be like plus or minus 20 nanometers on either side. So, because I doubt that you could get a detector to exactly detect 555 nanometers and ignore 556. I don't think we have that sensitivity level in our photometers. Okay, LCDs. LCDs have become the predominant type as opposed to a CRT, and the reasons are bulleted here. LCDs are less expensive to make. They take up less counter space because they're flat. They don't have a depth to them like a cathode ray tube. They generate less heat, and so your air conditioning costs actually drop with the use of LCDs in an indoor environment. They have a longer life than a CRT, and they require less maintenance than a CRT. So advantages across the board for LCDs. It's just a better technology. Okay. One disadvantage of LCDs is the restricted viewing angle, which is the cosine law. Brightness drops off dramatically when the viewer is not when the direction of your eyeballs and your line of sight is not perpendicular to the monitor and the plane of the monitor, then you're going to experience diminished brightness. And so leaning back in your chair in an oblique angle to the QC station and saying, yeah, that image looks good, that tech has no idea what the actual image looks like. They are seeing, first of all, geometrically distorted from their acute angle. Second of all, something that's about 60% dimmer than it's actually supposed to look like as far as registering in their field of view. So they have no idea. That's not real QC. 90-degree viewing angle from the monitor is recommended to see the intended broadcasted brightness. And that's the cosine law, and it's explained by this here, okay? Polarizing. Polarizing means that there are certain materials that can filter light photons such that, now we're only showing you one oscillation. You know that from physics class, a photon is a double transverse oscillation. It's an electric field oscillation and a magnetic field oscillation. For the sake of simplicity, in this drawing, we're only showing you the electric field oscillation. Photon A has a vertical oscillation of the electric field. The polarizer material allows vertical oscillations to go through. Okay, but photon B, the electric field, does not have a vertical oscillation. It's got a horizontal oscillation, and so the polarizer blocks it. That's how polarized lenses work. Like your fancy sunglasses that cost $60 more, that's because in addition to the tinting, it's only allowing one type of electrical like vertical electrical oscillations going through the material in addition to the tinting. So any sunshine that does not have a vertical electric field oscillation is blocked by the polarized lens, and that's why polarized sunglasses work so much better than just tinted sunglasses. Okay? So many different materials can exhibit this chemical property called polarization, where the light photons are basically sorted. It's a semi-translucent material, and light photons are sorted according to the character of the light photon as to if it's allowed to pass through or not. Well, an LCD takes advantage of this. Okay? In a liquid crystal display, we actually put two polarizers perpendicular to each other. Okay? And then what we do is we manipulate a liquid goo in between the two sets of polarizers to actually twist the photons to make them pass through. It's quantum engineering at the finest, folks. Okay, but a simplified version of that. Oh, here, if you have polarizing filters, like this gentleman is holding, if you orient them so that the polarization is parallel between one filter and another, then the light gets through, or 50% of the light gets through. So you can see in slide A, 50% of the sunlight is getting through. But if you orient those polarizers as they are in the diagram, such that the one polarizer is blocking horizontal oscillations and the other polarizer is blocking vertical oscillations, well, that's 100% of the light photons. And that's why in picture B, you can't see hardly any of the sun getting through the polarizers. And that's because you're blocking all the light photons. Because light photons will either have horizontal oscillation or vertical oscillation or some variance of those, where they'll be mostly horizontal or mostly vertical. Okay? And so opposed directions of two layers of polarizers blocks 100% of the light. But if polarizers are aligned, then 50% of the light can get through. Now, how does this work in a liquid crystal? Well, Carroll seems to disagree with Bouchon. Carroll says that the liquid crystal actually bends the orientation of the light, which could be true. But the easier thing would be is if the liquid crystal was an adjustable polarizer. And that's more in line what we understand the liquid crystal is doing. Okay? So like I said this morning, the liquid crystal is made out of long chain hydrocarbons. Okay? Organic molecules. So long chains of carbon. So the molecule definitely has a long axis. It kind of looks like a stick or a log. Okay? If those molecules are oriented a certain way, then light's allowed to pass through. If, however, their orientation is changed 90 degrees, then the light's not allowed to pass through. Now, the other characteristic of this long organic chain is that it's got to be polar. That is, it has to have an electron cloud surrounding the whole molecule such that the electrons tend to spend more time at one end of the chain than the other. And so the entire chain molecule, this stick, is said to have a positive and negative end, like a cathode and anode end. And it's just the orientation of the molecules and the fact that electrons, because the electrons are randomly, it's all covalently bonded, so the outer shell electrons are being shared fairly uniformly, but something about the way we built this molecule makes it so the electrons hang out at the one end 80% of the time and hang out at the other end only 20% of the time. And so the whole molecule takes on a polarity where it's got a positive end and a negative end. Okay? Now, if it's got a polarity and it blocks light in a certain orientation but allows light through in another orientation, then we can pass a voltage through it and get it to let the light through, or disable a voltage, turn off the circuit, and it blocks all the light. And so if we put it in a little chamber like this, then we have a light emitting pixel that we can turn on and off by regulating the voltage to that pixel. That's what LCD technology is. And like I said this morning, it sounds like some people were smoking weed when they dreamed this up. So we have linear shaped organic molecules with an electric polarity. That is, it's a hydrocarbon chain, but we have manipulated the end points of that hydrocarbon string such that the electrons like to hang out down on the far end more than they do the near end. And so the entire chain, the length of the chain, one end is a net negative and one end's a net positive. And that means if we apply a voltage across the liquid, we can actually choose the orientation of the molecule, because its own electric field, its own polarity, will respond to like capacitors. Like if say the whole LCD pixel was a giant capacitor, and we had a small positive charge on the front side and a small negative charge on the other side, well then the molecule is going to line up front to back. But if we turn off that voltage to that capacitor, then the molecule is going to randomly orient and just kind of drift, because it's a liquid, and liquids kind of, because of entropy, liquids kind of tend toward disorder over time, and the orientation of molecules in a liquid is random unless you do something to order it. Okay, so that's how we do it. That's how an LCD works. It's a goo, but the molecules that make up the goo respond to electric fields, and those molecules line up with the electric fields. When they do that, that changes them from opaque to transparent. Okay. Now, if we make these little chambers of goo really, really small, and then we put on a color filter on the front, and we backlight the little chamber, light comes through the back. Does the goo allow it? Okay, it travels through the front where it hits the color filter, and then it only broadcasts the color of the color filter. Okay, so we can get a red pixel, a blue pixel, and a green pixel. Okay, so they call it a nematic liquid crystal. Hydrogenated amorphous silicon. Long thread-like shape, that's what nematic means. And they tend to align with each other because they're polar, right? So just like if you had a bunch of magnetic rods and you threw them down into a box, would they pile up randomly like throwing galvanized nails into a box? No, they would align north-south, north-south, and they'd stick to each other. And so you'd have an orientation to the entire crystal because of the crystal having a magnetic field. Well, this one has an electric field. All of these nematic crystals, these thread-like crystals, have a positive end and a negative end. So the positive end of one is attracted to the negative end of the other. And so some of them line up positive up, and then immediately adjacent to that, the other ones line up negative pointing up. Okay, and then the whole crystal becomes neutral because there's a balance of charges. Until you apply a voltage across it, and then you actually get some of the crystals to flip over. Okay, now he says that they're all aligned with each other. You can reduce the density of this and put in some filler, like just some plain oil, some non-polarized oil, and thin them out and get them to actually randomly distribute rather than line up even when there's not a voltage on them. Okay. Light will follow the orientation of the crystals unless the crystals are made randomized, and then the light is stopped because there's no way through. Okay, the light will twist and pass through both filters. Okay. But whether you say the crystals orient with the direction of the light or they orient 90 degrees to the direction of the light, or the crystals, by their orientation, twist the electric field oscillation. That's a great question for a quantum physicist. All you have to know is the crystal changes its direction, its long axis orientation, and that affects whether light is allowed to get through the cell or not. That's what you need to know. The specific mechanism of how it does that, Bouchon says one thing, Carroll says another. I tend to believe Carroll rather than this, but I don't know, I could be wrong. Okay, so you can apply, so what is this little plus sign here, the hardware pixel and the flat wire? That's how you apply the polarization, okay? So you can charge the exit polarizer, and then that charge carries through the crystal to affect the orientation of the molecules. If you cut the power to that exit polarizer, then the crystal starts randomizing because it's still getting hit by light photons and entropy exists. And so the crystal orientation starts randomizing and the pixel cuts out because it has to be a uniform orientation of the crystals in order for the light to pass through. As soon as the liquid in the goo cell there becomes disoriented, you get randomization and you don't get uniform polarization twist or uniform flow of the light through the crystal. Okay, so applying the voltage allows light to pass through the second polarizer. Not applying the voltage, light doesn't pass through. Now, can you scale that? Yeah, we know what a rheostat is. And so we can scale the voltage with a rheostat, having a master voltage and then having parallel circuits come off for each row and each column of pixels, and then a rheostat, a micro rheostat, adjusts the voltage to each individual cell, affecting its brightness. So a partial polarization, remember, full polarization lets 50% of the light through. Okay. Partial polarization, you can get 25% or 10% or 45%. Okay, so you can vary the brightness of the pixel very much like a dimmer switch. Okay, which is also a rheostat. So each pixel can broadcast at maximum brightness or can broadcast at a fraction of maximum brightness all the way down to 0, because we can tune the voltage. Let's say we need 5 volts to get maximum polarization and allow maximum amount of photons. Well, let's scale that back to 3 volts. That's not 0, so some photons will get through, but not all photons will get through. There is some randomization of the goo and the molecules in the goo. Okay? 0 volts, complete randomization of the goo, none of the light photons get through. Okay? So listen to this over and over until you wrap your head around it. Okay? Oh, see, he says the exact opposite of me. I thought for sure it was you apply a voltage and that's how you get light to go through. But he says as long as there is no voltage applied to the exit polarizer, you'll get light. And so you actually need to supply it with power to turn the pixel off. I will do my best to not quiz you on that nuance on the test, but he's saying that when you pass current through this transparent conductor that's passing an electric charge from the polarizer into the goo, if you're not passing electricity, then light can come through. But if you push electricity into the goo, then that disables the ability. It randomizes the orientation of the crystal, or turns the pneumatic fibers to such an orientation that they block all the light. Okay. Right. So when the crystals are all lined up and they don't half twist, in his version, the light is blocked. It's only when you make them half twist by turning off the power that the light's allowed to go through. Okay. So if all the light is blocked, how is that pixel going to look on the monitor? It's going to be a dark spot. If 100% of it is blocked, then it's going to be black. Okay. And so as you scale up the voltage, or I'm sorry, because it's inverse, as you start turning off the voltage, by applying charge to the pixel, the light gets dimmer and dimmer and dimmer. So going from white to black is adding electricity to the pixel. All right, so that's great for black and white. We know how to get to black, right? Don't let any light through the pixel. We know how to get to white, let all the light through the pixel. If we make these things small enough, we can fool the eye into replicating, color vision. And the way that we do that is by coloring some of the pixels green, some of the pixels red, and some of the pixels blue, like you see in the upper right-hand corner of this slide. Okay? So a single pixel is actually 18 different subsegments. All right, so the pixel is actually 18 different cells, like we described on the previous slides. 6 of the cells are colored green, 6 of the cells colored red, 6 of the cells colored blue. Okay? And so 3 segments make a domain, a pair of domains makes a subpixel. So the green subpixel is 6 segments, or 6 cells. The red subpixel is 6 cells. The blue subpixel is 6 cells. Now, we make this infinitely small, and you are not an eagle, so you can't actually see the pixels. They're so small that they all blend together into a cohesive image. Okay, and we can vary the intensities. We can turn green off, and then what color would you see? Well, what's the combination of red and blue? Wouldn't that be purple? Yeah. We can turn off blue and just show you red and green. That's yellow. Okay. We can turn off green and blue and just show you red. And we can vary the intensities. Okay, so if we wanted to show you orange, yellow is maximum red, maximum green. But if I want to do orange, I'll do green at 50%, maximum red, 0 for blue. And so it's like yellow, but it's shifted and biased a little bit more toward red, so it appears as orange. Okay. Purple is maximum red, maximum blue. Okay. All right, so these pixels are extremely small. We can make all the colors of the rainbow by varying whether green, blue, and red is on or off, and whether they're broadcasting at maximum or some fraction of maximum polarity, okay, by varying the current to each of the exit polarizers. Okay, so for a monochrome display, like an X-ray, each subpixel can be treated separately as an entirely different addressed element. Okay, so we vary the voltage, that varies the current, and then the subpixels can, so you actually improve resolution by displaying a black and white image rather than a color image. For a monochrome display monitor, or one that is broadcasting a monochrome signal, we acquire 3 functional pixels in the same same physical place on the monitor for a single color pixel. So that means, again, when you're viewing black and white images on a color monitor, the software takes advantage of that and you get a native resolution that is 3 times the color resolution. Okay. Now, spatial resolution for display monitors, class 1 monitors, that's your radiologist, 3 to 5 megapixel monitors, that's your 4K, okay? So basically the rule is for classification of what's the difference between class 1 and class 2? It is 2000K. So anything above 2000 by 2000, which would be 2 megapixels, because 1,000 times 1,000 is a million. So anything above 2000 by 2000 is considered class 1. That can be your 3K, your 4K, your 5K. I think they've got 8K monitors now, but the limits of human vision resolution are actually 4K. So don't go buy an 8K TV. You'll have to get transplanted eagle eyes to actually see the difference between 8K and 4K. Your eyes are not powerful enough to actually visualize 8K. Now, 8K makes sense for radiologists because they have AI softwares that are overreading and looking for pixel aberrations. So higher resolutions than the limits of human vision does make sense in the medical field. It just doesn't make sense to watch Monday Night Football. Okay, an 8K monitor is no prettier than a 4K monitor. Just get the 4K. You're not missing anything. The people who are stupid enough to throw down the extra $2,000 for 8K, they're wasting their money. Okay, it's science. Your eyeballs are not that good. Okay? The whole reason digital image works in the first place is because your eyeballs are not that good. Okay? So, class 2 monitors, again, as low as 2 megapixels. The actual standard is greater than 2 megapixels is a class 1 monitor. Those are the ones that are used for diagnosis. You should not be diagnosing on a class 2 monitor. Okay. Class 2 workstations, those are, physicians can use those if they want a quick read by themselves. Okay. Some of the surgeons do. Some of the ER physicians do. They want a quick read of their own accord. That's their purview as medical practitioners. They can do so on a class 2 monitor. They should understand that the limitation of the monitor is affecting the clarity of the information displayed because there is a step off in resolution. Class 2 monitors are deemed high enough resolution that radiographers can use them to assess whether an image is diagnostic or not. Okay? Assessing whether an image is diagnostic and actually using an image for diagnosis, those are 2 different standards. Okay? Class 2 monitors are sufficient to assess, is this image diagnostic or not? So that's why when you're at your workstation, you can expect that it's a class 2 monitor. All right, liquid crystal displays, the liquid crystal does not glow. Okay? Every liquid crystal display is backlit. Now, the first versions were backlit by conventional incandescent light bulbs or fluorescent bulbs. The new ones are backlit by LEDs. And so you might see on the registry an LED monitor. That's just referring to the backlighting source. Okay, LCDs, all LCDs need a backlight because the liquid crystal does not actually, it's not the source of the light. It's only basically an adjustable polarizer. And so if you don't have a light source in back of the crystals, then there is no light to come through. So the modern monitors are switching to LEDs. LEDs, as far as efficiency of being a light source, LEDs don't generate heat when they generate light, and so there is no potential burn up of a filament or any of the components of the quote unquote light bulb, even though it's not a bulb anymore. And the LEDs take less electricity for the same, to broadcast the same brightness intensity as an equivalent incandescent bulb. If you converted your domicile or your apartment to LEDs, and they just made the incandescents outlawed last week. Congress did that, yeah. So if you've converted to LEDs, you might notice that the wattage rating on the LEDs are less than incandescent bulbs, and that's because they use less power to generate the same amount of light. And so LEDs as a light source, it's just a newer version of a liquid crystal display that uses an LED source, a light emitting diode, rather than a filament in vacuum or low pressure mercury vapor gas that's excited by electric polarity like you see in a fluorescent bulb. Nick Tesla invented that thing, by the way. All right, so adequate brightness, we're going to use LEDs. Typically, it's not just one LED, it is a strip or an array of LEDs, and that's the backmost layer of the LCD monitor. So if you had like a junk computer monitor that you were just going to throw out, you wanted to donate it to the school, I could very gingerly take that thing apart and I could actually show future classes the guts of an LCD monitor. Okay, I might actually ask our computer IT department if they have any old monitors that I could gently take apart. So, all right, so every LCD is backlit. The liquid crystal does not generate the light. It only chooses whether the light goes through or not. Okay. Active matrix array LCDs, that's what the Bouchon diagram said in this morning's lecture. The way that you control the polarization of the crystal by the exit polarizer is you hook it up to a TFT array. The TFT, remember, that's a transistor, so it acts like a switch, so it naturally can either deliver a voltage or cut off a voltage. Okay, if you have a control rheostat on the line, a semiconductor automated rheostat in line with the transistor, then the transistor can be set to open, but then the rheostat can determine how much current actually reaches the transistor and therefore how much polarization you put onto the pixel. Okay, so with this, because it is an electronic device, there's a response time and a refresh time. Okay, so a response time for a pixel is how much time does it take, and it's usually fractions of a second, for it to receive a new voltage input, but then actually change brightness. And so there's a little gap. And actually on my physics tie for semiconductors, it's called the CMOS lag time, okay? Is similar to this TFT array lag time. So you change the voltage coming to the transistor. You don't shut it off, but you change the voltage. Let's say you want to dim a pixel. Well, that's got to be an adjustment to the current going to. So you drop the voltage, the current drops by Ohm's law, and then the lower current starts passing through the transistor. That achieves less polarization at the crystal, and then the amount of light passes through starts to reduce. And so the response time is how long does it take for the cause, which is lower current, to produce the effect, which is lower brightness. Okay? It's still physics, and you're still manipulating physical objects, in this case the orientation of a chain hydrocarbon. Well, that's a motion, therefore it's a velocity, therefore it has a duration of time. Okay? If it has a duration of time, the duration of time it takes for the molecule to reorient is effectively the response time. Okay? Because the other player in this whole scenario is a light photon, and a light photon doesn't really have a response time. A light photon is instantaneous. 3 times 10 to the 8, it's the fastest thing in the universe. So we don't really talk about the response time being a lag in the light necessarily. It's the lag in the crystal orientation as responding to a different voltage and therefore a different current. Now, refresh time, you're going to a completely different picture broadcast on the monitor. So refresh time was going to look exactly like this. See how fast that was? Okay. So there's your control electronics. Okay. Electronics controlling current to each row of pixels. So there's there's an array of chips there and drivers. And it looks like there's at the very bottom, there's a linear stack of capacitors. And so the various circuitry on the green card is driving the individual voltage levels for the various rows. And then those black boxes at the edge of the LCD, those are sorting the various voltages to the various pixels. Okay. And then I'm sure there's a control, yeah, right in the middle of the top. So look at the top left image, you see the square chip right in the middle. That's the control chip. The LCD has its own CPU. Okay, it's got the capacitor arrays in the bottom right hand corner. Those are for storing reserve charge, like as a ballast, to either boost pixel polarization or drop pixel polarization by pushing more charge to a particular pixel in a particular transistor, or pulling charge away from a particular. So there's a capacitor array reserve to hold and bleed off additional charge as necessary to keep adjusting the level of charge to each pixel. So very much like a submarine determines how far it dives or whether it surfaces. This capacitor array is kind of acting like a ballast tank for the LCD, a reservoir of charge, if you will, so that it can pull charges away and hold on to them somewhere, and it can add charges elsewhere. Okay. So all of that's an active matrix array, in that it's a matrix, so it's divided into a grid, and each element in the grid can be chosen by that element's transistor to broadcast a lot of charge to the polarization cell or broadcast no charge to the polarization cell. Okay, so there's a capacitor at each pixel that prevents charge from leaking out, and so the LCD does not flicker between frames like a CRT does. It's a smooth transition without a flicker. So the next time I change slides here, notice that there's no flicker. It just, bam, almost instantaneously flips to the next slide and changes all the pixel assignments. Okay. LCD monitors have refresh rates as high as 240 hertz. So 240 times a second, the monitor is deciding what are the pixel values to broadcast. And that's why it seems like it changes from one slide to the next instantaneously. It actually takes 1/240th of a second for the slide for all the pixels to change. If we had a high-speed camera, we could actually see that. I wonder if they've done that, because there's the slow-mo guys on YouTube. I wonder if they've actually tried to capture an LCD screen refresh on a high-speed camera. That would be interesting to. I'll look that up and see. If we got it, then I'll include it as a resource. That would be cool to watch. So. Too much digital processing can cause input lag, delaying display. Okay, so input lag, if you've played video games, you understand what lag is. It's what gets you killed on Counter-Strike or Call of Duty. Is because your screen refresh rate is not the same as the host's screen refresh rate. He shot you half a second ago, but the information hasn't updated on your monitor yet. And so you think you're in an even gunfight with them, and then all of a sudden it updates and you're dead. It's like, what? Yeah, that's called a lag kill. And what's happening is the video feedback that you are getting is about 1/20th of a second behind the video feedback all the other players in the game are getting. And so you're being killed not because you're slower, but you're responding to information that everyone else had access to. You're actually playing the video game in the past. That'll break your brain. All right, on to the next. Okay, coming up on the 45-minute mark here. So active matrix array LCDs. Let's see what we say. Oh, yeah. Resolution. So the resolution is the dot pix or the pixel pitch. Now, what is the pixel pitch? I explained that to you. This is the distance between the centers of two adjacent pixels. Okay. The smaller the dot pix or the pixel pitch, the greater the resolution, the sharper the image. Okay. So images appear grainy when the pixels get too big. Okay. Think of Super Mario Brothers back in the 80s. It doesn't look like an Italian plumber. It looks like a stack of blocks. Yeah, that's poor resolution. Your pixels are too large. Okay. Modern monitors, high resolution monitors, or even 2K resolution monitors, things look fairly realistic so long as you don't zoom too high. Okay. All right. So how do we keep the pixels from squishing the goo out? Well, you don't. The LCD monitors are totally squishable. Now, don't press too hard because you'll actually ruin the monitor. But you can actually tap the monitor. Now, some of the newer ones have rigid plexiglass in front, so they're more resilient to physical stresses. But some monitors you can actually push and get a dark spot. So just put your finger on the monitor and push in and see if you see a dark ring start forming around your finger. And that's you're actually compressing the goo and you're affecting its polarity through compression. Okay? And so don't do that. You're going to ruin your monitor. Okay? Most dead pixels occur from this type of abuse, so LCD monitors are not meant to be touched. If they are physically subjected to poking pressure repeatedly, they get hot spots or dark spots where the cell has been crushed and it's not as thick as it used to be, or maybe even the capacitor is disconnected, or the TFT is damaged in some way. And so therefore, that pixel or that region of pixels doesn't broadcast as it should, and it typically shows up as a spot that's dimmer on the monitor. We can't have that in medical imaging, so if there is a damaged monitor, it should be replaced. Okay. LCDs are non-emissive display monitors. Optical effects are used to convert light from another source into graphic patterns. Emissive display monitors produce their own light, so plasma TVs, which are different than LCDs, thin film electroluminescent displays, and light emitting diodes, where the light emitting diode array is actually the display, not a backlit light emitting diode, LCD. Those are emissive displays. LCD is a non-emissive display. I would even call it a passive display because it requires an external light source to work. Okay. That light source is housed behind the monitor. Okay. Emissive display systems like plasma have not shown the quality for medical applications, so we can get achieve a higher resolution with an LCD monitor than we can with any of the emissive display technologies. All right, so we've talked about the LCD and how it's put together and how it works and how it's basically better in every way than a cathode ray tube. Well, there is some drawbacks to an LCD. There's a limited viewing angle due to the brightness lost because it uses polarized light that is being broadcast at a 90-degree angle to the monitor. You don't really get the light spread coming out of the front of the LCD rather. You get the cosine law, which I explained briefly in class, but basically the LCD is a device that's meant to be viewed with the gaze of your eyes perpendicular to the screen. Okay, so if the monitor is at an angle to you, the image is going to be broadcasting dimmer, or from your perspective, it's going to be less intense than it ought to be. And so it really doesn't make a difference for casual viewing, like looking at a PowerPoint slide. But when you're trying to image critique an X-ray, it makes a world of difference. The cosine law affects your ability to accurately assess brightness and contrast from an oblique angle. You have to view the image from a perpendicular perspective. Okay. Inability to transmit a true black. You can tell that with any time you have a black screen. Turn the monitor off and you'll notice it gets darker. And that's because the LCD screen always is backlit. You don't ever turn the backlighting source off. You just try to darken the pixel and block the light from getting through. Well, a tiny percent of the light still gets through, so it's a bright black, if that makes any sense. Okay. Brightness is time dependent and temperature dependent. The monitor kind of warms up to a maximum brightness, so just first turning the monitor on in the morning, the image is going to be dimmer than if it's been left on for an hour or so. Okay. Viewing angle. Luminous intensity describes the concentration of light at different viewing angles and is defined as lumens per steradian. So the display monitor is the weakest link in the imaging chain. A consistency between all monitors is essential. They all should have the same luminance, be set at the same contrast, and you should clean these things monthly. And you clean an LCD screen with isopropyl alcohol. Okay, so an alcohol prep pad is a perfect cleaning tool for an LCD monitor. The monitors have to meet the specs for DICOM Part 14. So if you're displaying medical images on a monitor, it should be, the contrast and brightness should be set to match the levels recommended by DICOM 14 or Part 14, and no one should be messing with the brightness and contrast of the monitor after it has been calibrated and set. Various test patterns exist. The two most common are the TG18 by the American Association of Physicists in Medicine, and then the SMPTE test pattern, which is probably the most popular, but the TG18 is specifically designed for medical imaging display systems. All right, so these are the two test patterns. The one on the right is the SMPTE. The one on the left is the Task Group 18 or TG18 from the AAPM. And so you can see that they started with the SMPTE pattern and they just added a few more tests to it and a few more specialized blocks in the one on the left. And that's to better gauge spatial resolution for structures, for anatomic structures. So it's got various test blocks all around the pattern. Class 1 and Class 2. Class 1 monitors are the only ones fit for diagnosis. They must have a native resolution of greater than 2K. Okay. Class 2 monitors are the ones the techs use for image critique and so image quality assessment. Those can be less than 2K. Okay. Typically, your radiologist is using a 4K monitor, and you guys are using right around a 2K monitor. It certainly doesn't hurt anything. Image critique and quality assurance measures of images can be done on Class 1, but it's overkill. Diagnosis cannot be done on Class 2, or it shouldn't be done on Class 2. All right, luminance rate. We talked about luminance, what a lumen means. It's 0.0015 watts, okay, and a watt is a joule per second. So it's the rate of light emitted scaled to 500, so the rate of light at 555 nanometers that's emitted from a light source, in this case the monitor. Okay, well, we need to know, for the lumen to be meaningful, we need to know about what area that lumen is being projected into, and that's where we get the definition of the steradian. A steradian is a cone of viewing area. There are, in a hemisphere, there's roughly 6 steradians. A steradian is an equilateral cone. That is, the length of the side of the cone is equal to the radius of the base of the cone. Okay, so it has very much an equilateral triangle shape in profile. It just has a circle for a base, and it's a 3D object rather than a two-dimensional object. So this steradian kind of maps to the human viewing area. And it's the closest, iridian is the closest 1/6 of a hemisphere. It's the closest representation to how much light coming from the monitor actually intersects your eyeballs. Okay. A candela is a base unit for intensity of light sources in all directions. Okay. So we're not talking about in the direction of an observer at this time. We're talking about the total intensity of a light source. How many photons is it pumping out? Okay. One candela will generate 1 lumen per steradian. Okay, so when you get 1 lumen of light flux, that is 0.0015 watts of power, joules per second of light coming at you in a steradian area, that is that cone that's right there, that's equivalent to a light source that is 1 candela strong. Okay. Now, how many lumens does the LCD monitor broadcast at? It has a maximum of 800. A CRT has a maximum of 600. A ViewBox has a maximum of 3000. Radiologist preference, which is not a maximum necessarily, it's just a survey of what they prefer, 500 to 600 lumens. Okay. So the LCD should not be broadcasting greater than 800 lumens. We need to check them annually, and we use a photometer to do that. Now, how do you build a photometer? Well, you have a photodiode or a photomultiplier tube or some kind of photodetective device hooked up to an ammeter. Okay? And so you pass a current through, right, a native current of a singular strength. Let's say we have a 2 milliamp current, but if it's got this photoresistor, that will cause the current to dip by inverse proportion. If we have a photodiode, it will cause, or a photomultiplier, both of those will amplify the current over the native current. So depending upon what type of detector you have, determines the adjustment to the current and then determines how the calculation is made to estimate the lumens or the candelas per square meters is often what they report. All right, so 2 types of photometers. There's a near range, stick that sensor right onto the surface of the monitor, or a telescopic. It's got like a rifle barrel or a cylinder, and the photosensor is at the end of the closed off cylinder, and the light is supposed to go down the tunnel of the cylinder. A telescopic photometer is held at exactly 1 meter from the monitor. Okay. Either type works just as well. You just have to use it as intended. Ambient light should be kept constant, so you don't change the ambient light when you're assessing a monitor. You measure it with the working conditions. So if the lights are usually on, you measure it with the lights on. If the lights are usually off, you measure the monitor with the lights off. Okay. The meter should measure luminance between 0.05 to 1,000 candelas per meter squared. Okay. The accuracy of the photometer should be plus or minus 5%. TG18 test patterns primarily, SMPTE test patterns are being slowly phased out in favor of TG18 test patterns. Okay. Now, the 5% that you're plus or minus 5%, that's not for the photometer, that's for the luminance response. So you test this thing when you first set it up, and you set the brightness and contrast level, you test it, it's in the appropriate DICOM range, and then you come back and you confirm that it's maintained its brightness and contrast over the course of the year, within plus or minus 5% agreement of what you measured last year, 5% of historic and baseline testing, okay? So maximum luminance, you just broadcast a white square and you test the white square, and it should broadcast at about 800 lumens, okay? Luminance response is the ability to accurately display different levels of brightness. So luminance response, maximum luminance is just testing maximum brightness. Luminance response is testing the variability of brightness across a grayscale. In other words, it's testing the ability of the monitor to accurately display contrast. So now, you have to know this part for the registry. DICOM says that the adjusted LUT values, which are called the p-values from the image data file, when they're converted by the driving software for the display to the digital driving levels, it's got to be a 1-to-1 directly proportional conversion. You're not allowed to have a monitor display driver that applies an exponential adjustment to the grayscale or to the native p-values. That's a manipulation of the image data, and it affects diagnosis. And so you can't have you can have a software that does that, but it's got to be reversible. And so a monitor display driving software is a non-reversible change, and so that change is not allowed. If you want to apply an exponential scale, that's just a different lookup table. You can reprocess your image and save it as an additional copy, but what you can't do is alter that image on the way to broadcasting it, because that's irreversible. There's no way to unadjust it, you see. And so if the digital drive, in the conversion to the digital driving levels, which are basically the voltage values for the pixels, it's got to be a directly proportional conversion, okay? So bright white should be, according to the Carroll model, should be the lowest voltage, and black should be the highest voltage in the digital driving levels. Okay. Maximum luminance should be greater than 171 candelas per meter square. Non-uniformity should be less than 30%. Okay. Now, what does non-uniformity mean? What's a test for non-uniformity? Well, you develop a test pattern that has broken the entire display into a grid of squares that are all the same color. And then you measure the luminance, so it's like some medium soft gray color. You measure the luminance and you check to make sure the luminance measurements at all locations on the monitor are basically the same luminance. If there's a greater than 30% difference, when you know the pattern is supposed to display the exact same color throughout, well, then you have a bad section of the monitor. Okay. Spatial resolution should also be verified on various locations of the monitor to make sure it's consistent. Loss of spatial resolution in any particular area corresponds to what we call a geometric distortion. Geometric distortions are more prevalent on CRT monitors than they are LCD monitors. So test for display noise and also luminance uniformity. Use a uniform gray test pattern. All 4 quadrants of this test pattern are duplicates. Every color tile has dots in it, but it's always the same uniform gray background. Okay. Fluctuations in luminance are attributed as noise. All right, so remember again, for uniformity, we want less than 30% variance. So if you measure any one of the tiles in this pattern and measure any one of the other tiles in this pattern, then you should not get more than 30% variance. Now all of them have dots in them of subtle contrast cues. So it can also measure for noise and contrast. Oh, how do I go to the next? Hang on. So, in addition to luminance, there's illuminance. Illuminance is the intensity of light striking a surface, so how well objects are illuminated. So luminance refers to a light source. Illuminance refers to an environment that is lit by a light source. Okay? So illuminance refers to the strength of the backlighting for the LCD. Okay? That would imply you would have to take your monitor apart to measure true illuminance. Okay? So the backlight source has a luminance, but it's illuminance with an I in front, is how much light is actually striking the glass substrate and the entrance polarizer to the LCD behind the monitor. Okay, the unit for illuminance is the lux, which is 1 lumen per meter squared. Okay, direct sunlight has 105 lux. Overcast is 103 lux. Full moonlight 10 lux. Radiologist reading room 2 to 25 lux. So very, very almost like 2% to 25% of what sunshine looks like. Okay. I know, more units of measure. Why? Why do we need all these? Well, I don't know. So they can ask you more questions on the registry. All right, so your SMPTE test pattern for luminance response for measuring contrast, adjacent squares, and the outer ring should all be distinguishable, along with inner squares of 0 to 5% to 95 to 100%. Okay. 50% of the squares should match. So as you're measuring the various luminance, see how it changes from 0% to 10% to 20%. That's the change in the voltage for the digital driving levels. And you should see that the luminance basically stair steps down in accordance with those increased percentages. So it should be a regular step in luminance measure when you measure the luminance response. It should be a regular increase in luminance of the same magnitude each time until you get to the 100% bright white. Okay. If any of them are outside of the regular pattern, So it should be an increasing straight line or a set of staircases if you're using a bar graph. If anything's outside of the straight line pattern, that means you have a variance, and that variance can't be more than 30%. Right? Now, the grayscale standard display function is based on human perception with increments of brightness called just noticeable differences. You might see, because this is what I can see, two brighter dots in this image. Okay, I think there's actually 5, but you can clearly see 2 brighter dots. You might also notice there's a little bit of noise in the image. That is, the background gray is not a uniform color. It's got flecks and mottles through it. But there's a dot in the center of this gray square, and there's a dot in the top right-hand corner of this gray square. And those dots are not perfect circles. They're kind of, I don't know, they kind of look like they've got flat sides. So luminance response should fall within 10% of the GSD grayscale standard display function standard. Okay, so just noticeable differences. Okay, adjacent squares on the SMPTE test pattern should measure 10% difference with each other on the photometer within 10% accuracy. Adjacent squares that are not distinguishable indicate insufficient contrast. Like, yeah, I don't know. I can see a just noticeable difference between 90% and 100%. So you should be able to tell the difference with a 10% change in luminance response. Okay, luminance ratio is the luminance of maximum, which is bright white, versus the luminance of black. Remember, the LCD cannot produce a true black while it's energized because it's completely it's always backlit, so there's always some light coming through the monitor. You can tell that black is actually less than true black if you turn off all the other lights in the room with a black screen LCD. The black screen LCD is going to be the source of light. Well, if it was truly black, it wouldn't be a source of light, but yet it's still the source of light in the room, even though the monitor is only broadcasting the color black. Right? LCD have poor luminance ratio, that is the difference or the ratio between white and black is pretty thin. Okay, black on white and white on black bars are used to measure luminance ratio. So you would calculate a luminance ratio for the top, black on a white background, and then you calculate a luminance ratio for the bottom, white on a black background. Those should be consistent, but they also should be a poor ratio. Okay, luminance uniformity. You're supposed to broadcast again. You're supposed to broadcast a uniform color across the screen, and then test to make sure you're getting the same luminance in every area of the screen. And this is the one it can't deviate. So for the contrast test, the maximum deviation is 10%. For the uniformity test, the maximum deviation is. So if you know the monitor is supposed to be broadcasting a singular color the luminance should be measuring the same at every location of the monitor. Anything greater than 30% variance is considered non-uniform, and the monitor needs to be adjusted or replaced. Okay, I gotta pause it, hang on. Types of reflection. Now, reflection is bad for a monitor. We don't want to see light from others. That's why ambient light is frowned upon, is because it produces reflections. So anytime you have a piece of glass or a piece of plastic that's clear, it's possible for a light photon to enter, especially if it's a flat surface. A light photon can intersect that surface, and at the point of intersection, it can do two things. It can rebound back, which is reflectance, or it can pass through but change direction, or it can be absorbed. And passing through and changing direction, that's refraction. So reflect, refract, or absorb. Okay? We typically don't want reflection. We would rather it passes through. Okay? Or absorb. So the LCD monitor, by virtue of it being a double polarizing filter, actually allows for better transmission than most objects. And so while it's pushing light out towards you, it's also taking in light from the room, and that light is just depositing on inside the monitor somewhere. Okay. It doesn't reflect light all that well, but it still does. Now, most LCD monitors are equipped with an anti-shine coating to limit specular reflections. Okay, so let me tell you the difference between a specular and a diffuse reflection. A diffuse reflection is just a bright spot where you have an overhead light on, you're looking at the monitor, you can't really see the shape of the light, but you see like a glare. But the glare doesn't have a form, it's kind of fuzzy. You just know that there's a brightness coming from an alternate source. Okay? Specular reflection is where you can actually make out like shadows and shapes and details of the contents of the room. Okay, so if you can see a silhouette of your own head in the monitor, well, then that's a specular reflection. Okay, if you can see the outline of the door to the hallway, if you can see another monitor that is in back of you, all of those are specular reflections because those are reflections from the room that don't belong on the monitor. They're not part of the image that you're trying to see. You know that they're reflections, but you can also tell exactly what those objects are. They're either light sources in the room or it's illuminance. That is, the light source in the room is bouncing off of an object, and then I can see the object or the silhouette of the object in the reflection on the monitor. So that's a specular reflection would be something like if you were a spy and you were trying to use a television to, like, let's say you're just chilling out having a meeting, and all of a sudden you look over to a monitor and you can see in the reflection of the monitor someone is coming in through the side entrance and they're carrying a gun, and so that tips you off. A diffuse reflection wouldn't be able to tip you off like that because you'd only see like a fuzzy bright spot, like a shine or a haze type situation. So diffuse reflections don't have physical form that represents the objects that are being reflected, that are part of part of your viewing environment. Specular reflections, you can actually make out the source of the reflection. It's an actual object in the room and how light is displaying that object in the room. So specular reflection is when your LCD is trying to make itself into a very poor mirror. Okay. Right. So because both specular and diffuse reflections are bad because they affect our ability to actually, view the X-ray we're trying to view, these things are ambient light sources must be kept to a minimum in a radiologist's reading room. The reason they have the lights off and the doors closed is not because they want to take a nap, although they do take advantage of that. But it's not because they want to take a nap. It's because they know ambient lighting produces reflections that affect their ability to view the images. So a haze or a bright spot, if you've ever played video games, you understand this intuitively, okay? If there's a window or a glass door behind your television and behind your head when you're trying to play video games on your television, you're constantly going to see a specular reflection of that window somewhere on your monitor. And if that's where the bad guy is and it's a multiplayer shooting game, you're not going to be able to see him. You have kind of a blind spot and he's going to be able to shoot at you. And so you have to be aware of that when you're playing a video game that, oh, I can see the specular reflection of that window. That's handicapping me in my proficiency in this video game because I can't see that part of the monitor as well. So hopefully you position your television, if you're serious about video games, you position your television such that you also minimize specular reflections on the monitor. Okay. LCDs again have low reflectance overall, and they usually have anti-reflective coatings on the front. The modern monitors do. Right, ambient light versus veil glare. Ambient light is environmental lighting. Any light source that is not the monitor is considered an ambient light source. And now I really like this picture because the man happens to be bald. And so there's a perfect example of a diffuse reflection right on the top of the man's head. See how it's a little shiny right there by his hairline? That's a diffuse reflection. There's an overhead light source that is bouncing a reflection off of his scalp, but I can't make out the definitive shape of the light source. It's just a hazy glare or a highlight, okay? So that's a perfect example of a diffuse reflection. Veil glare is when you don't properly black surround mask your diagnostic image and there's white pixels in the edge around the image. And I think I've got an example of veil glare and how it affects contrast coming up. Yeah, here it is right there. So so as you're watching this, if you're doing it on your phone or on your PC, just go into a room where you can shut all the lights off and really look at this slide, okay? And compare the two. You should subjectively feel that the one that's surrounded with white is darker overall and has poorer contrast than the one that is surrounded with blue in this case. That's supposed to be surrounded with black, but apparently I surrounded it with blue. Okay? You should be able to see Now, unfortunately, what you can also see is either noise or a dirty image receptor on the left one that's surrounded by the dark color, but you can also make out so much better the palm of the hand and the soft tissue border on the left side image than you can on the right side. It's still there on the right side image, but it doesn't look as clear. It doesn't pop as much as it does on the left side image. And the only difference between the two is that one is black surround mask or dark surround mask, and the other one is not. Okay, and so this is why this is what's called veil glare. Okay, on the image intensifier, it's called veiling glare, but this is called veil glare for a digital image. The white, remember, your eyeballs view relative brightness. So the pure white surrounding the X-ray, you perceive that as brighter than the structures in the X-ray. And so all of the X-ray looks darker because you're comparing it, your eyeballs are comparing it to the bright white border. Okay? If you eliminate the bright white border, now the X-ray appears brighter overall. So for this reason, that's why the radiologists prefer the black surround mask, is because, and so that gets rid of the veil glare. They also turn off all the lights in the room and close the doors. That gets rid of the ambient light. Now the only light that they're considering is light coming from the X-ray itself. All right. There's no quantified guidelines for acceptable levels of noise in the radiographic image. There's a pattern test for just noticeable differences. This suggests the passing point is the dimmest dot, must be visible in at least 3 of the 4 quadrants on the screen. Okay, so they have this test pattern where there is a low contrast, there's 5 low contrast dots, 4 of them in the corners, and you ought to be able to see 3 out of the 4 dots. If you can't see 3 out of the 4 dots, that means you have too much image noise. There you go. So this is exactly the exact same test pattern. One with an extremely noisy monitor and one with a mildly noisy monitor. All of them have 4 dots. So that looks, it's like a 5-sided dice, both of the images. Now you might say, well, I only see 2 dots on the left. There's 4 dots there. Actually 5 dots there. Okay. Keep looking and you'll be able to make out the other ones. Now in the right hand side, can you see any dots? Maybe you might say that there's an argument for a dot in the middle, and there might be a dot in the top right, but the rest of the image is too noisy to make out any other dots. Okay, so increasing noise reduces our ability to spot low contrast differences, and so this is the standardized test. This just noticeable difference test tests for the noise level of your monitor, but ultimately it's subjective, and ultimately it's up to your radiologist how much noise is tolerated and is not tolerated. So I think we can all agree the right side is non-diagnostic, but is the left side truly non-diagnostic? Some radiologists would say, yeah, even the left side is too noisy. Other radiologists would say, no, that's probably right there at the threshold. Right? ACR and American Association of Physicists in Medicine recommend a minimum display resolution of 2 line pairs per millimeter. Okay? And that's both horizontal and vertical. So when you measure line pairs per millimeter from a monitor, you have to do a vertical spatial frequency test and a horizontal spatial frequency test. because a lot of times it's not the same number. A lot of times monitors have a better vertical spatial frequency than they do a horizontal spatial frequency. Okay. Both the SMPTE pattern and the TG18 pattern are capable of testing, of calculating. They have a line pair test pattern embedded in each. Okay. For a class 1 monitor, oh, sorry, the font's so small on this one. For a class 1 monitor, 15 or fewer bad pixels across the entire screen. So if you broadcast a raw beam, if you shoot a raw beam, raw exposure, and then you bring that up, should be uniform gray across the thing. Okay, and you will have to mag it up and then pan through it to see if there's any pixels. So magnify it up so you can see individual pixels, and then start panning through the entire pixel matrix to see if anything stands out as a different color to you. Okay. 3 or fewer bad pixels within a 1 centimeter circle, 3 or fewer bad adjacent pixels. Okay. Less stringent guidelines apply for class 2 monitors. So that's the class 1. That's the ones the radiologists read on. Those are the ones that are probably going to be evaluated for bad pixels more often than class 2 monitors. Okay. Even still, if you notice an excessive amount of bad pixels on what's supposed to be a flat field on a particular monitor, but you pull up the same image on another monitor and it's just fine, then that's how you isolate the monitor, by trying to broadcast the image on several monitors. It should look consistent across all monitors. So if you see bad pixels that are reporting either just black, or which is basically null, no value, in a field of uniform gray, you should call in Biomed and have them take a look at it. Okay. Viewing angle dependence, cosine law. So the luminance at increasing viewing angles is one of the major disadvantages of LCDs. The brightness, the intended broadcasted brightness, drops off to, oh, I can't see, let's see. In as little as 30 degrees, you're down to 50% of the intended brightness. So inside 30, if you're just at 30 degrees off of true perpendicular, you're at 50% brightness. At 45 degrees, you're somewhere around 25% of the intended brightness. So again, there's no way that tech that's drinking coffee and just leans over in their little office chair and approves the image from an oblique angle, yeah, they're suffering from the cosine law. They're only seeing about 25% of the intended brightness. There's no way they're properly evaluating the image. Get your lazy butt out of the chair and look. It's only the patient's health and well-being that's at stake, that's all. Remember your ethics, for God's sakes. Repeat analysis. And this is the reason why image quality seems to be suffering in the digital age. This is the reason why technologists aren't particularly strict on the students regarding repeats. Most retakes are now due to positioning errors. We've virtually eliminated retakes due to faulty brightness and contrast because we can adjust that post-exposure if we need to. Rejected images are usually erased at the worker bee level, the technologist level, and they're not put into a bin of rejects. It's not like film screen where there's a permanent record of the awful, just god-awful image you just took. because it's a physical piece of plastic and you're required to put it in the bin. And then your manager goes through the bin at the end of the week and looks, who shot this crap? Even if it's a reject, yeah, thank you for rejecting it. But why the hell did you shoot it? Because it shouldn't have turned out like this. Yeah, those are the type of conversations we used to have. Okay? But the digital age has made things faster, quicker, more. One more patient, push them through, get another one done, 5-minute turnaround time. Is anyone tracking quality anymore? It doesn't seem like it. It seems like throughput or nothing. And that's just one of the problems I have with the way we run diagnostic imaging these days. All right. If we, and by we I mean the department managers, because they would be the ones that would actually have to exert their will and make this happen. If they would enforce that, we could start tracking the reason for rejected images. But they have to keep track of it. They have to watch it. They have to hold their technologists accountable. And so good luck. But if we do that, we figure out, is it a problem with the way PACS is receiving the data? Is it a problem with the X-ray equipment? Is it a positioning error? Is it ignorance on the part of the technologist? Yeah, Carol's too polite to put that in there as choice 4, but that is choice 4. Okay. So manufacturers are starting to answer the call and put in more specific software for repeat analysis. But as long as images can be discarded and lost so delete, wipe from existence, this event never happened type situation, the technologist can always cover his shoddy work or her shoddy work and pretend it didn't happen. And meanwhile, that shoddy technologist that's not learning anything because we don't have real quality analysis continues to overexpose patients because their repeat rates are higher than the people that actually know what the hell they're doing. And so there's a real effect of not doing repeat analysis. The real effect is patient populations are experiencing increased unnecessary dose because no one's putting the technologists in check that just keeps doing ridiculous amounts of repeats because they don't know how to shoot them in the first way and they don't understand the technology. A realistic threshold for repeat rates is the same as it was for screen film, 3 to 5%. Okay? If you're rejecting more than 5% of your images that you exposed, you're practicing with negligence. You should fix that. You should be embarrassed, and then you should fix that. And if you're a manager running a department and if you're not doing repeat analysis and you're not holding your techs accountable to image quality standards, you're the problem. Congratulations. Just a quick review. Units of measure. Luminous flux, or lumens, the intensity of light from a source. Illuminance is how bright is the light as that source broadcasts on a surface. Luminance intensity is through the viewing area, that is the steradian. Okay. Oh no, luminance intensity is the total light from the source, so that is candelas. And then luminance, where the viewing area has a defined boundary, the steradian, candelas per meter square. Okay, so 1 candela per steradian is 1 lumen. Or 1 candela will broadcast 1 lumen per steradian. Sorry. Candelas per meter square is a different unit of measure. So that looks like 4 different units of measure that they can ask you about on the registry. Am I going to ask you about those on the upcoming quiz? Yeah. All right, this is all we covered. Make sure you understand how an LCD pixel works, okay? How it polarizes the light and how it twists the light when it allows light to pass through. It's twisting the orientation or the polarity of the light, and that's the oscillation of the electric field. It goes from vertical to horizontal or horizontal to vertical, depending on how they got it set up. Every LCD has to be backlit so the light pushes through the liquid crystal. The liquid crystal can be translucent, that is, can let light through, or can be opaque, depending upon the voltage that you apply to it, which is the digital driving level for the pixel. DICOM says that when a software converts the p-values from the image data file to the digital driving levels for the monitor pixels, that conversion has to be a directly proportional conversion. There can't be any logarithmic or quadratic or exponential applications to convert to digital driving levels. Okay. Various test patterns for various types. There was luminance uniformity, just maximum luminance, which was 800 lumens for an LCD. Difference between class 1 and class 2 monitors is the native spatial resolution. And the definitions for ambient light and veil glare. You should know those too. All right, that's long enough. I'm going to send you guys this.